Hello everyone, my name is Piotr Wygocki and I came here from Poland and I'm going to talk about how to design C++ implementations of complex combinatorial algorithms. And in order to do that, I'm going to design implementation of the local search method. And but here I do not assume any domain-specific knowledge, so I'm going to explain what the local search is, and we are here to talk about C++, not about optimization. So everything's supposed to be included. I mean everything concerning optimization, and it's supposed to be also easy. So ask any question if something's not clear. Okay, so this is the outline of the talk. So first I'm going to introduce you to local search. It is actually crucial to understand this because later on we are going to discuss the design decisions, and they are of course implied by the used model. So this is going to be easy and it's important to understand it. And so after our framework is designed, we are going to focus on the more specific usage, and here I'm going to show you more complex usage of the library. And when we are done, I'm going to show you maybe some part of implementation, maybe more idea of the implementation. So let's go. Okay, so I'm going to talk. I'm not going to just give you formal definition of local search. Actually, there is no formal definition because it's rather a name of whole group of techniques. And also, in order to just give you intuition what that is, I'm going to show you just two examples. The first one is very basic one, very easy, and the second one is more real-world case to show you that it might help you to solve more complex problems. So what is local search? We've got a function which is supposed to be maximized, and you've got one specific point. And here we see that this is not the best point because, for example, this one is better, yes? And this one is even better. So what can we do to improve our solution? The simplest idea.
Trace along your data set until you hit where you start decreasing it?
Yeah, so what can we do? We just move our point a little bit to the left or a little bit to the right and check if that improves our solution. Yes, and this is very simple idea, and this is the main idea of the local search. Yes, so we have two possible moves here, and we call this neighborhood of this point x. We can move it to the right or to the left, and we see that this point to the right is better. So we modify our solution and we go on until we are in the so-called local maximum. This point is called local maximum, and you see that this method is not perfect because we didn't reach the global maximum. Yes, so this is just heuristics, but sometimes that's all we have, and this one works very well in many practical cases. So, and this point is called global maximum here. So it's supposed to be very easy and very clear. So are there any questions? Okay, so this is the main idea, and when you think about it, you can always think about this picture, although the use cases are going to be very, very different from that.
So a local search just finds the next local maximum or local minimum, that's it? That's the definition of local search?
I'm not going to give you strict definition, but this is local search is a method of optimizing our function. Yes, and this method assumes that we have like initial point, and the idea of improving this point is just to explore the local neighborhood of this point and in this neighborhood we try to find the better points, and we just go on. This is, yes, I know that this is not very like strict definition, but I think this is good definition for this talk. Yes.
Well, one note: depending on the size of your neighborhood, you might not even end up in the real local maximum.
Yes.
But still, it's a useful technique.
And here I'm going to show you pseudocode and what's going on here. So let's focus on this inner loop. Okay, so we've got some initial solution x. This is our starting point, and we explore the moves in the neighborhood of x. Here we check if our move is improving. So if there is a gain of applying our move on our solution, and if yes, we apply this move. And we just iterate this procedure. And this actually illustrates one specific strategy in the local search, because here we find the first move that improves our solution. And this is not the only strategy, because we can, for example, find the best move that improves our solution. Yes, but this is one particular strategy in the local search. And I'm going to talk about this in more details later on. So this is just to give you like the idea. Is it clear? Any questions? Okay. Now I'm going to talk like about more sophisticated example. And this problem is called facility location. And in this problem, we would like to locate some number of facilities. So they might be hospitals or parks or this kind of things. So each of these points represents the place where we can build a facility, and also a place where are the potential clients of this facility. So now I'm going to give you the formal definition, but later on I will just show you an example, and example I think explains everything. So in this facility location problem, we've got two possible costs. So the first cost is the cost of building a facility. That's kind of self-explanatory, obvious. And second one is transportation costs, and it is defined as, for each facility we define transportation costs as the distance to the closest chosen facility, and here we consider the total transportation cost as just sum of all of these costs for the clients. If it was not clear, just don't worry and check this example. So here we decided to build two facilities, the red one and the blue one. And the cost of this red one is $30, the cost of the blue one is $40. And now for each client, we connect this client to the closest facility, and this distance is measured, and here this distance is $5. Yes. And here is the same, and this distance is a little bit like bigger, so it's $8, and so on, so on. You've got the picture, and our total cost is just the sum of all these costs. Is it clear? Any questions? So it looks more like real-world problem. Yes, it's still toy problem, but it's like more like real-world problem. So how to solve this problem using the local search method? This is the question. So we can represent the solution of this problem. It can be represented by the set of chosen facilities, yes? And we would like to modify this set a little bit and check if this improves our solution. So any ideas? How can we modify this set? Yes, that's right. So we can, the first possible move is to add one facility which is not chosen, and we check that if the other possible type of move is to remove the facility, and there is swap move. This is more complicated, like we open one not chosen facility and close one that is chosen. Yes, and of course we can just, there are many other types of moves that you can consider. So, and actually we've implemented this algorithm. We've got some use cases, and this problem is very hard. In general, we don't know how to solve this problem efficiently. It's NP hard. It doesn't matter what it means. And for our use cases, this local search which uses these three possible moves, it's very often finds optimal solution. So it works, and if you just use only these two moves, you're just within 5% to the best one. Of course, on some set of instances. So, and also you might see that real-world cases are complicated. So here we've got two possible costs, but in real-world case, you can have like 20 possible cost functions, and you know the idea is still the same. You can still use this local search, and it works. And you can add number of constraints, and you can treat one facility in a special way, and it's very easy to write this local search algorithm still. And that's why it works very well in real-world settings. So now we are going to design our library. And so here are our main goals. Yeah? So it's supposed to be easy to use. That's kind of obvious. If someone decided to program it in C++, he cares about efficiency for sure. So it's supposed to be efficient. And also, our research showed that other local search libraries, like they perform many like additional computation. I mean, you would like to make something very simple, and this other frameworks perform many additional computation, like computing some advanced statistics or like creating new threads and this kind of things. And here we just assume that our algorithm is supposed to do exactly what it is designed to do. So what is desired to do. So this is kind of important here. And loose coupling, this means that entities that are not dependent in that are independent in semantic way, they should stay independent in the code. And I'm going to give an example for that. And extensibility, so it's supposed to be easy to extend the once written code. And also it's supposed to be easy to extend the code written by some third party. Questions? And we are going to focus on this goal later on. So let us focus on like something very easy. So there is this first improving strategy that I told you about. So this strategy just iterates over the moves and find and try to apply the first move that is improving. Yes, and we are going to implement only this simple strategy in the beginning. Is it clear? And these are like conceptually, these are the things that we need to know to implement our algorithm. And so for a given solution, we need to know what are the possible moves that can improve this solution. And for a given solution and given move, we need to know how good this move is. So it returns delta, which if it is positive, it means that this move is improving. If it's negative, it means that this move is non-improving. And if we decided to really apply the move, we have to know how to do it. And this is this commit which takes solution and a move and try to apply this move on this solution. And this might be not successful, so it returns a boolean. So this is kind of important slide because we are going to use these signatures all over the presentation, yes?
So it's valid to return in the moves range something which isn't really possible to move into? Otherwise you wouldn't.
Yes, kind of. We've got use cases for that. So, but you don't have to worry too much about this. So you can think about it that it's always successful, more or less. But the point is that this commit might have some probabilistic behavior inside. So it could, and this could cause this not successful commit. This is first reason, and the second reason that might be some in the multi-threading setting. The solution might be like changed in the meantime, and this move just became not valid or not improving or something like this. Okay, so let's move on. So this is the first idea, yes? So this is the first improving algorithm. It takes reference to the solution, to the current solution, and it takes these three functors with the signatures that were introduced in the previous slide. And this is all in this local search namespace. I am going to use this ls all over the time. So
this is extremely dependent on where you start, right?
yes, that's right. So very often you like to choose random starting point and just repeat it a couple of times. The question was, this is very dependent on the starting point. That's right. So, is it clear? It's supposed to be clear. And so, this is like possible implementation of this. I don't know if you, this is like very straightforward. Just to, so here we've got like this inner loop. We just traverse all the possible moves. We run the gain functor to check if the move is improving, and we try to commit this move here. So we use all of these functors, and we just repeat it in the while loop. And you have to return if at least one iteration was successful. I just didn't want to include this here. So it's possible to implement. It's very easy, and it is, I think, quite easy to use because we have only three functors here, and it's supposed to be efficient because it's, yes, this function can be just inlined. It's in header file. It's so we have to answer just two questions. Okay, loose coupling. There are no real dependencies here, so let's omit this. And we have to answer the question how to extend this code. So assume that we would like to print. Okay, we wrote these functors, someone wrote these three functors, and now we would like to run our local search and print each move that was committed. That's reasonable. So how to do this? So we write print commit adapter, which uses our previous commit and just returns whatever this commit returned, and we print the move. So the answer to the question how you extend this library is just by function composition. It's very simple idea, and we just run our local search algorithm and providing the previous get moves, previous gain, and this print commit adapter. This is the way of extending one's written code. Questions? Okay. This is easy for me, and I don't want to lose you guys. So maybe this is like trivial, and that's why there are no like questions, or this is very not clear. This is simple. That's great. That's what I was expecting, and this component is very loosely coupled. That's what I meant. So this is like totally independent of the problem definition. Yes. So there's only one constraint. This move has to be printable, and that's all. So that's what I meant by loose coupling, and we are going to write our component this way. And we think that this is a very cool way of writing our components. And okay, so what are the problems with this design? The problem is that these three functors might be dependent, and the worst case is that, for example, this commit functor like assumes that we used some specific gain functor. They might be dependent. This is not always the case. Actually, in most of the cases, this is not the case, but it might happen. And this is like very bad because we definitely want to keep them together. So somehow encapsulate this. And if you like look at this interface, this even looks like object-oriented interface. There's a solution in the beginning always. This looks like C-style object-oriented interface. And also when you just wrote facility location, and this is the end user. He just want to run local search on facility location. So he just didn't want to provide all of these functors. He just want to say, just give me all of this facility location stuff, and that's all. So this is just arguments for that maybe we should somehow group these guys together. And so the first idea is maybe this just should be function members of the same class. That's kind of obvious idea. And this is not the best idea, actually. Because when you want to write like good local search algorithm, it involves a lot of experimenting. So you just very often write many versions of this get moves functor, many version of gain, and many version of commit, and you just try to mix them together, combine them. And if you wanted to use this object-oriented approach, you would have to, in this situation, you would have to write 100 classes, because you just essentially need all of these combinations. There are some ways of reducing that, and this is not very nice. And also, adaptation, our way of extending library changes to inheritance, and this is creepy actually, and we don't like it. We like the previous version, so we don't want object-oriented interface. So what can we do? So the first idea is to group them together in one class, but not as member function. Just this class is actually a tuple, something like tuple containing these three guys, but we can provide like nice interface for calling this, and nice way of creating this component. This class is called components. I think it's not the perfect name, but I just don't have a better name. And we can have like functions to replace one of the components here. So this is the first idea. So, and now this interface looks like that. So first we have to create these components, and then we just run local search providing these components. So no real gain here. It just looks almost exactly the same. But this one is better, because if you got this facility location components once grouped, we just can run it this way. So it looks a little bit better, maybe. So what are the problems? Actually, we must be aware that what we've done doesn't really create a new value. There are these two approaches. We can pass these three arguments separately, or we can just pass them in one object. And what we've done is just combination of these two approaches. And there are still the same problems here, actually, because still, if we've got two functors that are dependent, the user still can replace one of these functors. It is just harder to do that. So, but let us assume that it is sensible and we just don't know how to make it better. And yes, that's true. But so what we do not like about this implementation is that this kind of trivial. We've got another frameworks in our library, and this is not very generic solution. It's because we have to write this class like from scratch, from the beginning. So we actually introduced our own. Yeah. So the problem is that it's not very scalable solution. So we're supposed to just use some kind of generic solution. So, for example, use something like Boost Fusion map to just keep them together. How many people knows this Boost Fusion? So, essentially, what we've done is almost the same, but with nicer interface that just works well in our use cases. And as I said, this class over here is essentially a tuple. And so we can just use std tuple, but std tuple has this like ugly interface for retrieving elements, and we don't like that. So we would like to have our own data structure and with possibility to retrieve elements by name, and with some other functionalities which are sensible here. So we introduce our new class, which is called components. Now it's components not in local search. This is just generic solution. And I'm going to show you how to use it. So first of all, you need to introduce the names of the components. So here, these are these three names: get, moves, gain, and commit. And later on, we just need to write this fourth strange line, and you're done. That's all you have to do to use these components. So now we've got components in the local search namespace, which does essentially the same what the previous implementation of components in local search was, and we are using our generic solution components here. I don't want to explain this line. It's just some variadic templates and some template aliasing. And how can we use it? We can now construct our components, providing implementation of these functors. Are you with me? So is it clear? Any questions? Just do not hesitate to ask. And here we assume that these implementations are default constructible, but this is not general assumption. I'm just going to show you a couple of use cases, and we are done with components. So this is the way of retrieving components. We just provide the name of this component, and we can retrieve it. We can set another implementation of the components with the members set, and we provide the name of the component. And we can directly call the component, also providing the name and the arguments. And we can replace one of the component with the component with different type that gives us totally new components class. So this is the way we use it. And we are actually pretty proud of this components class, and there are much more like interesting use cases and much more functionalities, but unfortunately we do not have enough time right now to discuss this. So it was like small off topic, and now let's get back to our design. So now we are just using this components class, this generic class, and everything just looks essentially the same. So we just call our first improving, provide reference to solution, and we provide our local search components. So what are the problems here? Okay, the previous problems were, for someone at least, there would be like not very important. So who cares if we pass like 3 parameters separately or grouped in one class? So I mean, who cares? But actually, we've got like quite serious efficiency problem in this design. I think it's not very obvious if you haven't seen that before, but maybe some ideas what might be very inefficient here.
It's not exactly simple to go through all your implementations. You have to set it every single time once you go through, when you're looping through your implementations.
I think I don't understand this.
So every time that you switch one of your implementations, right, and then you have to go back into your into the function that you've called, you have to again manually go through that every single time, which is inefficient.
Did someone understand this question? Because okay, I'm supposed to repeat the question, but I quite don't understand it.
We select only one implementation, right?
Right, but I mean, I'm guessing you're going to have more than one implementation.
So yes, but you are passing your solution by reference, so it does not actually cost you. This first observation, and second observation is this function is probably going to be inlined anyway, so it actually doesn't matter. And okay, this is not the case, so I'm just going to. The problem is that these moves can have various types, as in this facility location, and so do you remember this facility location? It has 3 different types of moves, and each of these types is represented by different C++ type. It's probably represented. And how to implement this get moves functor? So it's supposed to give us a range of all moves, but these moves can have different types. So this is kind of problem, and we've got to handle this problem. So we can handle it using dynamic polymorphism, yes. So, or we can just create some strange class with enums. So we've got one class, and it has enum inside which says I am add move or I am remove move, and this is creepy. We don't want to do that. And if you write gain and commit functors, this is not cool anymore, because this gain functor has to check what is the type of given move and then delegate the task to the appropriate place. So you can see that it is not nice to write these functors, and also it might cause inefficiencies, which is maybe even more important. And we can, yes, is it clear? So how can we solve this problem? This actually, the idea is very easy. So now we can have components for each type of move, and library should just somehow handle it and make it efficiently. So now we've got components for add, and this guy here just contains these 3 functors, as the same as before, and this guy over here is the same, but this is 3 functors assuming that the move is add. And now our first improving is just variadic template, and it's supposed to just do it efficiently. And we also gain like additional flexibility because we can now very easily remove one type of move. We can like just change the ordering, or we can like double this one. And this might look strange, but sometimes it makes sense to do that. For example, if there is some probabilistic behavior inside of this. So we gain like some flexibility here. And this is actually the end of the design. So now I want to show you like typical implementation. So we always need the model. So this class which represents our solution. And in this case, we just introduced an interface which has 4 member functions. This member function add facility, which just adds facility to the solution and returns what is difference in the costs. And the analogous one is remove facility, and we've got just 2 member functions to retrieve unchosen facilities and chosen facilities. And this is the implementation of functors connected to add move. And I just don't want you to understand this code, although it's very simple. I just want to just show you that it is very easy to implement this. It fits into one slide. And I made all of these templates because we just want to reduce dependencies in our code, but they do not have to be templates. So the end user does not have to write templates himself. Yes?
In that case, I'm wondering about the complexity of add and remove facility. Because if I remove a facility, for example, I have to recompute all the distances. So I think that this is an expensive operation.
Yes.
And you'd need a different interface to get the gain. So then you'd need, 2 solutions, for example.
But we've got like exactly, okay, the question...
It works with the interface, but the facility location gain add doesn't seem efficient.
Okay, the remark was, the observation was that it looks like inefficient because we have to, sorry, not this, but this one. Mm-hmm. Because we have to recompute all of this cost, and maybe we're supposed to just, maybe we can like gain something if we just do these 2 guys together. Yes? Yeah. And that's right observation. This is just toy problem, and you can just, if you want to optimize it, you can optimize it. And yes, that's right. And this is just like toy problem, and this may be not the best. I think it's a very nice problem actually. But yes, the observation is valid. It might be valid also, although I actually implemented this way. This is almost actual implementation. And I think you cannot gain, you just, there are no benefits of doing this together, as far as I know. Maybe if you've got like better idea, we can discuss this online. Okay, so we finish our design, and this is the place where we should ask ourselves the question for end user: is it worthwhile to use this library? And so what can we gain? What are the benefits? And even someone might say that the code is well structured and so on, and you also gain some flexibility with managing different kind of moves, and the library just makes it efficient, and this is not maybe so obvious how to make it efficient in an efficient way, but on the other hand, the user has to understand this library, read documentation, and so on and so on. So I think at this point it's not very clear if it's worthwhile to use this library. Do we have like real benefits? And in the next section, I'll going to show you what are the more specific usage and where is the real power of this library. So how just we're still gonna use only these 3 functors, and we are going to build like much more complicated algorithms on using only these 3 functors and the library. And that's what, in my opinion, is the real power of this library. So there are many different like strategies in local search, and I'm going to explain them to you. The first one is called hill climbing. So this is like the very simple and obvious strategy. We just only choose the improving moves. So why should we change this strategy? So why should we like accept the move that is not improving?
Search a larger space.
Excuse me?
You can potentially search a larger space.
Yes, you can search larger space. So you can get stuck in this local maximum, and you just want to leave it somehow. So there are many like different strategies which accepts also non-improving moves. And the first one is like very trivial. It's like opposite to the hill climbing. It's called random walk. So it just accepts each move. It looks strange, but sometimes it's reasonable. And there is another strategy which is called simulated annealing. And as far as I know, this is like the most popular strategy, and it's very useful in practice. So this one is worth noticing. And in this strategy, this is very rough description, like very rough. But with small probability, we accept also non-improving moves. So there is like random process which decides which if the non-improving moves are accepted, and usually improving moves are always accepted. But this is not clear as well. The last idea is the tab search, and this in his like very basic version works essentially like random walk, but it remembers like some number of the previously visited solution, and it tried to avoid the solution. So it's like avoiding cycles in your search. So these are like the most popular, as far as I know, strategies, and I'm going to show you how to implement them in the library. So we'll start with simulated annealing, and we like always we assume that we implemented these 3 functors: get moves, gain, and commit. They are like exactly the same as in previous cases, and we are just going to use them to write like more complex algorithms. Okay, so now I'm going to explain you in more details what simulated annealing is, but it's still going to be quite rough. So in the simulated annealing, we choose non-improving moves with some probability, and this probabilities depends on 2 factors. And the first factor is like quite obvious. So the moves that are better have bigger chance of being accepted. Yes, so this is kind of obvious. And the second factor is a global factor which is called temperature. And the idea is that when the temperature is high, the non-improving moves have bigger chance of being accepted. And if the temperature just tends to infinity, this simulated annealing works like more or less like random walk, because all of the moves are accepted. And if the temperatures tends to 0, it works like hill climbing, more or less. And the idea is to start with big temperature to allow like wide search, and while the time passes, the temperature is lowering. This was like, I know, like quite rough description of simulated annealing. There are like many details that are there, and now I'm going to show you how can you implement this strategy in the library. So first of all, you need to know what is the current temperature. So, and how does it change? And this is usually named cooling scheme. So this is the name cooling. And now our temperature is like always equals 5. This is like pretty stupid cooling scheme, but we are going to work with that. And all we have to do, we just use the gain adapter from the library. We provide the previous gain and the cooling scheme, and we received our new gain, which we call gain simulated annealing gain, and that's essentially all. And we run our algorithm, and it just works. So actually, I think this is like very cool, because actually there is like the cost of implementing this particular simulated annealing was like there is almost no additional cost. So you just write cooling, you just create adapter and just run it, and that's all. And as I said, this cooling scheme is like pretty stupid, so you probably should use cooling scheme from library. And oh, this looks like terrible. It's exponential cooling scheme dependent on iteration, and someone might say that, okay, user has to understand what this function means, and this like looks like complicated. But this is like general problem in simulated annealing and in local search in general, that in my opinion, if you want to successfully run this algorithm, you must more or less understand what's going on in the like behind of this. So this is not, in my opinion, not like black box, and it's hard to bypass this assumption. Any questions?
Well, so the parameter in cooling must then match the magnitude of the gain that you typically expect. Because, well, the gain could be arbitrarily small or large.
Yes.
If you want to do this randomization, you must not overdo it on the range of the gain.
Oh, okay. The remark was, as far as I understood, that this range of this cooling, it's somehow connected to the range of this gain. And of course, this is right. So as I told you, you must understand what is going on here, and here you provide these parameters, and they are of course strictly connected to your problem, to your current problem. You cannot just take the defaults and just hope it's going to work. You just need some experimentation, or just you have to rethink that. That's the case. That's what was I actually said before. Yes, so you just must be aware what's happening here. So when you work with algorithms like simulated annealing, they just explore our like. It might be the case that they found like very good solution, but because of unlucky sampling, the algorithm leave that solution and end up in much worse solution. It just might happen if you are unlucky. So sometimes you might want to just, each time when you find like the better solution than the previous best, you just want to record it sometimes, yes? And here's the way of doing that in the library. So we just got another adapter from the library, which it's called record solution commit adapter, which just takes previous commit and takes reference to the best, and it will just going to update the best each time we improved our solution, the best solution. And of course, it's not for free, so because this introduces additional copies. So sometimes, so it's up to the user if you want to use it. But by default, we are not recording the best one, but it can be easily done. So I think you've got the idea. We just all the time we just writing these adapters, and they can be composed, and it just works. So there is this table search, and in the table search, as I told you, you just remember some numbers of previous moves, and you try to avoid them. And that's all. You have to write another adapter, and it works. So this time adapter this is the gain adapter, and it takes previous gain, and it needs a data structure to remember these moves. Yes, so this is a container, or something like container, which actually this one remembers last 20 pairs of solution move. And of course, here we use some table list from the library, but of course it can be replaced with the user-defined table list. It's just very simple concept. It has two member functions. I think we shouldn't just go into details unless you want to. And we just run here. We just provide previous get moves, this gain table, which is computed here, and the record solution commit, which was introduced before. And just compiles, and it works. Any questions? And what happens if we want to combine these two strategies, combine table search and simulated annealing? That's nothing easier. We just compose these two functions. So now we create our table gain adapter and provide this simulated annealing gain, which was introduced before, and just you compose them. You run it, and it works. You can do it other way around, and it actually means something different. And this is like very flexible, and you can use it. And okay, so these were like specific usage, and by implementing them, I just wanted to show you that this framework and this design is very flexible, and it's easy to extend it, and it's very easy to implement like standard algorithms used in the local search. Any questions? So we were working on this only one first improving strategy like all the time. So we iterate through the moves, and we take the first move that is improving. But there are of course other strategies. So there is this best improving strategy, which takes the best improving moves and actually takes the best move, check if this is improving, and if this is improving, it applies the move. And there is the first strategy, which just takes the best move and apply it. So it could be on improving. And from our experience, actually, these three strategies covers like all the cases that we were able to think of. And even if you actually think of something fancy, it can be like, at least from our experience, reduced to one of these three strategies. And all of the previous examples, all of the previous examples, you can replace this first improving with either this or this, and it just works, and it compiles. It does not always make sense to do that, but it's just fully compatible. And there is also like very general version, so you can, of course, implement your own strategy if you want to. So here you can use one of these 3 strategies. And there is like also some other kind of additional stop conditions or some additional action which can be performed after each round of local search. So this local search is actually useful because of these additional arguments. And if you really want to, you can implement your own strategy as well. I'm not going to details how should you do this. Any questions? Okay. So now I'm going to show you how can we implement this, or what is the main idea of implementation. And here we are going to focus on the best improving implementation. We are talking mostly about first improving, but this one is actually much more interesting. So that's why we are going to focus on that. So what this algorithm must make. So we've got 3 ranges of moves. These moves have different types. And for each of these moves, we need to compute the gain. So there is a delta, which if it is positive, it means that this move is improving. And later on, we just compute the maximum of this list. And if the best found move is improving, we applied this move using appropriate commit functor. Is it clear? And all of these delta types should they be the same type? And yeah, it is written like they are the same, but actually we need to only compare these types. So we do not want to impose any constraints that are not really needed. So the only assumption is that we need to compare this, and this. So these ranges could be actually of different types, consist of elements of different type.
How do you choose your how many adds and how many removes and how many swaps you're going to do? Is that just all possible?
These are just like normal runtime ranges. Yes. So.
Oh, okay. Yeah, I got you.
But like number of possible type of moves is like compile time. So in order to do that, we are going to focus on like much simpler tasks. So we are going to print the maximum of polymorphic list. And although this looks like much simpler task, it actually has all of the problems of the previous task. So if you're like were totally lost in this local search, and this is the nice point to start listening again, because it's like totally like independent problem. So now we are going to focus on very, very easy problem. So we've got the list containing of three elements. They are of different type, and we would like to print the maximum of this list. And how to do this? So I think like you can imagine many implementations, like direct implementations using some templates. It's actually not very hard to do. But here we would like to use like some really nice abstraction, that's reusable abstraction. And we choose the function which is called fold. And this is actually a well-known construction for functional programming. And we all know fold because this is like essentially it does the same as std accumulate. Who heard about fold before? Okay. Still, there are a couple of people. I'm going to explain what happens here. So if this is our sequence, in order to compute fold, you just run our functor on the accumulator and first element of the sequence, and this gives us the new accumulator, and we use this new accumulator and we run our functor with this new accumulator and the second element of the sequence, and we just iterate this. And the last accumulator is the result of our fold. And this is like very simple construction, but it's actually very powerful, and you can build many other algorithms on top of fold. So we are going to use this algorithm to print the maximum of the polymorphic list. So assume that we've got some implementation of this fold, and the essential part of our work is to implement this functor here. So we are going to do this. So this is the implementation. We've got the functor f. It takes the accumulator, which is the best one found so far, and this is the next element of the sequence. And if our new element is better than the previous best, we return the new element, and we return previous best otherwise. It's like very easy, isn't it? But actually this code is wrong. It's not going to compile in some case. Okay. Can you see the problem?
Best need to be comparable with none. For one.
No. I mean, even if they are comparable, it's...
So that's a requirement.
No, yes.
Be convertible. The return type, if best and number are different types, what type does it return?
Yes. So, okay, I'm going to repeat both the question. The first remark was they must be comparable. Yes, and this is our assumption. But assume that they are comparable. The problem is that we don't know what is the return type of this function. The point is, even if this type are convertible, I mean, one of this type is convertible to another, it still doesn't going to work in this setting. So this is like a problem. So the problem is that in C++ we cannot return like one function cannot return values of different types. So we would like to bypass this problem somehow. And in order to resolve this problem, we are going to introduce like slightly modified fold. And it is called polymorphic fold, and now instead of normally fold takes functor, accumulator, and sequence, and now our polymorphic fold is going to take accumulator functor and accumulator data instead of accumulator. And what it does, it actually delegates all of the work to this fold. So here this fold takes functor, accumulator data, and two iterators to the beginning and the end of this sequence. And so now we are going to focus on the implementation of this fold. So this fold has two overloads of parentheses operator. The first one covers the case when our collection is empty. Yeah, so we've got these two the same types here. And in this case, we just call accumulator functor providing accumulator data and return that. So this was like the simple case. And there is another case where when this collection is not empty. So we still run our functor providing the first element of the sequence, current accumulator functor and current accumulator data. And this functor is supposed to return new accumulator data and new accumulator functor, but it cannot do it directly because of this problem with types. So now instead of returning this type, this functor is going to call new functor which is called continuation. And this is the way to bypass this problem of this functor returning things of different types, because this functor might be something that can take arguments of different types. And the question is what this continuation is supposed to do. Is it clear what is happening here? What is the main idea? So this functor is supposed to return new accumulator stuff. And now instead of returning accumulator stuff, it's going to call continuation providing this new accumulator stuff. And the question is, I do not ask about the code, I ask like in semantic way, what is this continuation supposed to be? Any ideas? Any questions? This whole construction is actually not very semantically like trivial, so I think it's nice to like think a little bit what it's supposed to be. Any ideas? Nope.
Or we could call it a visitor because it needs to accept a range of types and do something with it.
The comment was it's supposed to call a visitor. No, we just want to make something like redirect. It's supposed to just it's supposed to recursively call this fault with the next element. Yes, so we're supposed to increment our iterator and just go on. This is what's supposed to happen, and this is the way how to achieve this. So continuation is just ourselves with this functor, and we increment the iterator pointing to begin. And it looks like really creepy, but it really works. And what is the point? It's hidden inside of the fault implementation, so it's our utility. So once we implemented this, we can use it. And the usage is actually very simple. So the implementation is creepy, but who cares? I just want to give you some time to parse this, because at least for me it's not like very trivial. Are there any questions? So,
can you go back to the slide where you have the first one you showed that didn't work?
yes, sure. Or maybe I can show you the slide with the functor that is actually working. Oh, okay, I can just go. Oh, sorry, not this way.
Yeah.
Yes.
So if you return the ternary num less than best, return either num or best, it's just going to deduce the return type, and that works.
What can you do to just okay
So ternary, like condition, question mark, true value, false value.
I think it's not going to work.
It will work.
The
The ternary must have a single expression type.
Right, and it'll deduce the common type between your two arguments,
If there is one.
if there is one.
okay.
if there-
So
it's where
the comment was that you can write this, as far as I understood, like
yeah, return.
number. Yes, and one.
colon
Yes.
test.
Yeah, yes, I just don't remember. I don't use it very often. And now if we can convert one of the type to another one, it might work.
No, it'll work if they have some sort of common type, and then you specialize.
Yes,
to
but
common type.
it might work. So, and you can maybe, if this doesn't work, you can maybe do it in some other way. But this imposes like additional constraints that there is like a common type, and we do not want to impose this constraint. And in our solution, we only impose the constraint that they are really comparable, and it doesn't have to. The common type doesn't have to exist, and this is the main difference. So your implementation is probably going to work in many cases, but this implementation is a little bit more general. Is this clear?
Yeah.
Okay, so I hope it is more or less clear, and now let's see how to solve our original problem, that is how to implement our functor now. So now we are doing essentially the same. So now our accumulator data, it is currently the biggest number, and now instead of like returning the new best number, we call continuation, and we provide this number, and we also provide the functor which just prints this number, and we just return the previous accumulator functor and previous accumulator data otherwise. So the implementation of this fault was creepy and scary, but implementation of this functor is actually almost the same as before, and that's what matters here. And we can call it. So we call our polymorphic fault. We provide this functor. We provide like boundary condition. So here we just print that collection is empty. We provide this like special element which is smaller than everything.
So what's the type of minus infinity?
The type of minus infinity is minus infinity. It is just like struct which has template operators, comparison operators, and it's smaller than everything. It is actually pretty easy to write. To write simple version of this, I actually try to extend this, and it's not so easy anyway. So this is like, okay, we could like, we doesn't have to make this way. We can just write an if here, so check if the collection is empty, print if it is empty, and take the first element and provide, if this is not empty, we can take the first element and put it in here. But I like this solution with this kind of, I think this is nicer.
By the way, so continuation is hypothesized on the functor n.
Yes.
Number or egg data.
Yes.
Is the number and egg data could have different types, right? That was the presumption.
Yes.
That means that the type of continuation is different depending whether you return first or secondly. So how does
That's right.
this work versus the previous example? Because here the two
Because we do not, this is function call. This is not object. Oh, maybe this is not clear. This is not object of type continuation. This is function call, and this is template function, which it was.
when then it returns the same time. Okay, got it.
Yes. So this continuation was this bind, and this is actually
Yeah, I see.
template call.
Yeah, I mean,
And so we've got assumption here that all of this accumulate functor, all of them must return the same type. So we've got this assumption, but it's not very constraining. So we did it, and we use exactly the same technique to write our best improving. Okay, so maybe I'm supposed to speed up. And it's a really interesting exercise to see what's going on here, really. So assume we've got this call, and let's denote n as a number of different types. So here we've got 3 different types. We only use int, float, and long. And m is the number of objects passed. So here we've just passed 7 objects, 7 different objects. Clear? So how many template instantiation we are going to have in this call, more or less? And the answer is many. Like, so if it's n times m, more or less. And another interesting question is, what happens if compiler decides to inline all of this function, like here? So how big code it is going to produce? And this is like scary because it's going to produce like the code which is exponential in size of the code. And yes, this is like what? And actually, I just didn't make like real cases, so I just didn't, because I didn't check what compilers really does. So this like, if you can compute it like on paper, but because in our use case, actually, this vector is like, has usually at most 3 elements, so we just don't care so much. But it's like, at least for me, it's like interesting observation that you can like pretty easily write a code which later on can be in exponential size after compilation. Any questions? Okay. And this is almost the end of the talk. So there are other local searches libraries when we done some benchmarking. So this like the simplest hill climbing, and there are these different libraries that we found that are written in C++. And ours, of course, is the best one, and it's like much faster than this one. And the reason is that they actually, okay, and in this test we were working on like n queens problems, so we just want to put n queens on the chessboard in the way they are not attacking themselves, and it's like well-known toy problem, and it's very easy to compute this gain and commit and this kind of stuff. So the most of the computation time is actually in library. So that's important in this comparison. And this algorithm were like totally the same. So they started with the same solution. They finished in the same solution. They made exactly the same moves in the way to the solution, and we are just faster. And also, it's hard to measure which design is more complicated. There are like no hard measures, not many hard measures. We measured how many functions do you have to write to program like very simple hill climbing. And in our case, you must write more or less 3 functions. And this is like the results for our for other libraries. Let's just focus on easy local. You have to write like 7 classes and 19 member functions to write like this hill climbing. So of course this is like not maybe the best measure, because in our library you just have to use this components class, and maybe this is not very standard, so it's harder to understand, and so it's not so clear that you know that maybe this in Mathlib you just have to write only 1 class and 5 member functions, and but still we think that our design is very reasonable. And we are getting to the end. So this is the web page of our project. This was only one framework. We just implemented much more, many nice algorithms. We are currently working on nice interface for linear programming. So just please visit it. And also we are very interested in any comments and remarks and any problems. And if you found something like not very intuitive, just please contact me. And thank you. So, are there any questions? Okay, so thank you very much.